Hi there, folks. Today we're looking at surface areas of pyramids and cones. And a pyramid is a special kind of polyhedron where basically we have a polygon base and then triangular lateral faces. And those triangular lateral faces will come together at a single point at the top of this pyramid. All right. A regular pyramid, which most of the pyramids we're going to deal with will be regular pyramids. Basically just means that that base polygon is a regular polygon, all right? And the effect that that automatically has is if that's a regular polygon, the lateral faces, the triangles that form those, will automatically be isosceles triangles, okay? It's just kind of the nature of what happens in order for these to come together at a single point. They have to be isosceles triangles. And really, they're all congruent isosceles triangles because their bases are all the same because they're the sides of a regular polygon. Okay, and so again, a pyramid, it's got a polygon base and triangle sides that meet together at a single point. A regular pyramid just means that the base is a regular polygon, which automatically makes those triangles isosceles triangles. Okay, so here's an example of a pyramid when we look at this guy. This is looks like either a square pyramid or a rectangular pyramid of some type. If this is a regular pyramid, then this would have to be a square pyramid. Okay, and the formula that's written off to the side over here, this guy, this applies to regular pyramids. Okay, this works when we have a regular pyramid because essentially we're just assuming that all of the triangular sides, those lateral faces, are the same. Okay, so assuming that this is a regular pyramid, meaning this guy down here is a square, we can use this formula for the lateral area, which just says 1/2 the perimeter times L. And L is like the slant height or the slant length. And that's the basically like the altitude of the individual lateral face. So when we look at the triangle that forms one of these faces, the altitude of that individual triangle would be this guy right here. It's this line that kind of travels up the side of that thing. Because again, if I were to kind of take that triangle off to the side and draw it, that triangle would look like this. And that line in red would essentially just be the altitude of that individual triangle, okay? That's what we're looking at when we look at the slant height or the slant length, okay? So that's what L represents. And again, that lateral area, that formula only works for regular pyramids. Okay, if we don't have a regular pyramid, we essentially just have to look at each triangle individually, find the area of each triangle individually, and add them up to get the lateral area, just like we did with our prisms. Okay, with the prism, the lateral area was the area of all the lateral faces, and that's the same thing here. That definition hasn't changed. So if I have an irregular pyramid, I just have to find the area of each of those individually and add them up. But if I have a regular pyramid, all those triangles are automatically the same. I can use this shortcut, this formula, 1/2 the perimeter times the slant height. Okay? And then, of course, the surface area is just the lateral area plus everything else that we have, which in this case is just that base. And when we use a capital B, we're indicating the area of the base here. Okay? And again, that's not different than what we had with the prism. The prism, the only difference was I had 2 bases, so I had to add that amount twice, okay? But here I only have 1 base, so I'll just add the area of that 1 base to the lateral area, and I'll have surface area, okay? I'm just adding up the area around the outside of this thing. For example, if I look at this guy, it says find the lateral area and surface area of the regular hexagonal pyramid. And so again, if you look at this and you realize that, okay, it's a regular hexagonal pyramid, so I can use that formula that was stated previously, and that's this guy. That's the lateral area equals 1/2 the perimeter times the slant height. All right, you could do that, or you could literally look at each of these individually. You could say, hey, let me look at this triangle that forms the side. And when you look at that triangle that forms the side, you could find the area of that triangle. It's got a height of 9. It's got a base of 6 because, again, this is a regular hexagon, which means all of these sides for the base are 6, which means all the bases of these angles are 6. You could find the measurement of that particular triangle and say, hey, the area of this particular triangle, well, once again, it's 1/2 the base times the height for the area of a triangle, so that's going to give me a 27 square feet. But then the thing you have to realize is there's more than one of those triangles. There's actually 6 of those triangles. So if you found the area of each of them would be 27. So then the lateral area, you'd have to multiply that 27 by 6, and you'd actually get 162 square feet. Okay? When we use this formula, we get the same thing. It's just a little bit of a shortcut. I don't have to think as much about the whole process. It's just say, hey, the perimeter of this guy, well, all the sides are the same. The perimeter of that base is 36. The length of the slant height is 9. And you can just plug that right into a calculator. When you plug it into the calculator, that's 162 square feet. Okay? So again, the lateral area, that formula is a nice little shortcut if we have a regular pyramid, but you can just look at each of the sides individually and say, okay, if this side is this much, how much is the next side? Add them all together. Okay? In terms of the surface area, I need to add the area of the base. Okay? And the area of the base this time, when we look at this thing, the base of this thing is going to be a hexagon. It's a regular hexagon. Well, to find the area of a regular hexagon, it's 1/2 the apothem times the perimeter. And so once again, we're going to use that perimeter of 36. But I need the apothem for this one. And this is where maybe some memorization would be really helpful. If you don't have that memorized, it's okay. Okay, you might maybe just remember that from when we did hexagons in terms of the angles that you have to use and that kind of thing. But if you don't, take it off to the side and draw this. If I'm looking for the apothem this time, again, if you kind of think about this being split in terms of triangles, okay? Remember the angles inside of a hexagon add up to 720. So each of those angles is 120, which means just half that angle. This guy is going to be 60 degrees. And so remember, the hexagon was one of the really nice ones, one of the really special ones, where we could do a 30, 60, 90 triangle here. So this is a 30, 60, 90 triangle. We know that this side over here was 6 total. Each side is 6 feet, so this is 3 feet and 3 feet. So now working my way around this triangle, the apothem this time is going to be 3√3 using my special right triangles, okay? And so that might take a little bit of thought. You're going to have to take it off to the side and maybe draw this thing, but the apothem is going to be the 3√3, okay? And again, that's going back to how do I find the apothem of a regular polygon? Using this one, I can do special right triangles, okay? And so now I plug this guy in. Again, this is probably a job for my calculator here, multiplying some of this stuff out. Looks like it gives me a 54√3. Notice I'm leaving it in terms of the radical for right now. That's square feet. Now let's find the surface area. The surface area, I just add these two values together. Okay, so 162 plus the 54√3. And now this is where I'll go ahead and let the calculator round it off as a decimal. Okay, if I wanted it in exact terms, this is done if it's in exact terms. Like in terms of the exact measurement, it's this. Okay, I can't simplify that any further. All right, and really that's not an answer that makes a whole lot of sense from the perspective of finding the surface area of this thing. So we'll plug it into a calculator. And we get 255.53 square feet. Okay. For this one, the pyramid of Cestius in Rome is a square pyramid with a height of 36.4 meters and a width of 30 meters. What is the surface area of the pyramid? And so, with this one, it might be helpful to draw a picture of some sort. And so for this one, if I kind of draw a picture of this thing, do a dotted line for the back of this. And so again, it says it's a square pyramid, which means the base is a square this time, okay? And it says with a height of 36.4 meters. And so that's the overall height of this thing from top to bottom, okay? And a width of 30 meters, which is kind of this measurement down here, okay? And so there's a couple of things we need to do. First of all, we can easily find the area of the base. That's not a problem. We want to find the area of the lateral area. The problem that I run into here is what I have is the actual height of this pyramid kind of down through the center of this thing. Okay, that's the 36.4. And what I really need is kind of the length of this along the diagonal. I need that slant height instead. And so what I need here is my Pythagorean theorem. When you kind of think about that triangle that I've drawn kind of floating inside this pyramid, here's what it looks like. It looks like this. And this is the 36.4. This bottom side is actually 15 because it's half the width of the pyramid because that drops right down through the center. And so the actual slant height would just be this missing value in terms of my Pythagorean theorem. Okay. And so using my Pythagorean theorem, let's see, the 36.4 squared, I'm just plugging it right into the calculator, plus 15 squared, gives me a 1549.96. And I'm going to take the square root of that. And notice I'm just going to leave it like this for right now. I'm not ready to plug this into my calculator, but that's the length of this, the slant height of this thing, okay? And again, just using the Pythagorean theorem to find that. Anytime we have the actual height and we need the slant height, we can use the Pythagorean theorem. Likewise, if we have the slant height and we need the actual height of this thing, we can use the Pythagorean theorem. And so now, once again, because the base of this thing is a square, that's a regular polygon, I can use my lateral area formula, which is 1/2 the perimeter of the base. The perimeter of the base this time is 120 meters. And then the slant height this time is the one we just identified as the square root of 1549.96. Okay? And again, I'll go ahead and start plugging this in. That's going to be a 60 square root of 1549.96. I will eventually round that off, but I don't want to round it off quite yet. I want to make sure I have the entire surface area, and then I'll plug them both in at the same time. Okay, so the surface area is just that value. It's that lateral area. Plus the area of the base, and the area of the base is just 30 times 30 for that square, okay, or 900, all right? And so once again, now this is where I want to go ahead and jump to my calculator. So on my calculator, I'm just going to do each of these, the 60 root 1549.96, and that gives me this guy. And again, I just waited till the end so that I wouldn't have to go back and maybe punch this thing in again. I have that punched in right now, and that's square meters. And now without even rounding this off on my calculator, I can easily just add the 900 or the 30 squared, okay? And that gives me 3262.17 square meters, okay? So again, find the lateral area. If it's a regular pyramid, we can use that special formula. Just make sure you have the proper height. We need the slant height, which is that height up the diagonal. All right, we find the lateral area, and then surface area is just a matter of adding the area of the base. A cone is very similar. A cone is basically like a pyramid with a circular base, okay? It's not considered a pyramid because, once again, those lateral faces are not the proper polygons. They're not triangles this time, okay? And it's kind of the same kind of comparison we had between a prism and a cylinder. They're really the same thing. They act the same way. We find things the same way, but they're slightly different because they don't fall into that definition of a polyhedron, okay? So a cone is a solid that has a circular base and a point not on the same plane as the base. It looks like a pyramid. It acts like a pyramid in every way, shape, or form, but it's not a polyhedron because we don't have those triangular sides, that kind of thing. So that's why it's not a pyramid, okay? So it's like a pyramid with a circular base. The lateral area is pi r L, where once again, L is that slant height off to the side over here. So it's that diagonal height going up the side of this thing. And really, that's kind of the same thing we were dealing with before, where the slant height is 1/2 the perimeter times that slant height. When you think about it, the perimeter for a circle is the circumference, which is 2 pi r. So 2 pi r is the circumference. If you do half of that, times the slant height. That's where this formula comes from. It's literally the same formula of 1/2 perimeter of the base times the slant height. It just so happens that the perimeter of a circle is 2 pi r, and when you simplify that, the 1/2 and the 2 cancel out, so I'm left with pi rl. Okay, so pi times the radius times the slant height. All right, the surface area, once again, is the lateral height, the lateral area, plus the area of the base. So same thing, it's all the same stuff. We just have a special formula because circles have special formulas for perimeter and area, okay? They deal with the radius, they deal with pi. For example, if I look at something like this guy, it says find the lateral area and the surface area. And so once again, the lateral area is 1/2 the perimeter of the base times the slant height. For a cone, it ends up whittling down to this special thing of pi r l. Okay, pi times the radius times the slant height. And so for this one, pi r is the radius, which is 15. L is labeled, that's the slant height, that's 25. And again, I'm just going to leave this in terms of pi until I'm ready to do any kind of decimal approximation. So in terms of pi, that gives me a 375 pi square centimeters. So there's the exact lateral area. And now the surface area is just the lateral area, which I just found, plus the area of the base. Well, the area of the base, that's a circle. And to find the area of a circle, it's pi r squared. So pi times r squared, so the radius squared, so that's the 15. And now it's just a matter of simplifying. And again, I'm leaving this thing in terms of pi because, one, I might want to find the exact area of this thing. But two, it's always good to wait till the end, wait till I have everything before I plug it into the calculator and round it off. When you look at it, that's actually a pretty nice, neat answer. And so, again, that's the exact values of these things. If we want the decimal approximations, now is the time to plug that in. But again, I'll kind of do each of these separately. So I'll do the 375 times pi on my calculator. And once again, I'm using the pi button on my calculator. So the rounded off answer is 1178.10 square centimeters. Over here, I'm going to separately punch this in, 600 pi. Again, I'm not using the rounded off answer. I'm starting with an exact answer and then plugging it in and rounding it off. Okay, that's it. There's the lateral area and the surface area, both the exact value and the rounded off value. If we look at this one, it says in a chemistry lab, you use a conical filter funnel as shown. How much paper do you need to line the funnel? And so when you look at this thing, here's the dimensions of this particular funnel. And once again, they give me the actual height, this actual height going down into the funnel. But what I need is this lateral height. Okay, and so once again, if I kind of think about this triangle that they've given me, the dimensions of this triangle, we've got the 45 over here. This side would be 40. It's half the distance across here. I have to use my Pythagorean theorem in order to find this. So 40 squared plus the 45 squared on my calculator gives me a 3625. And again, you could try taking the square root of that to see if it comes out nicely, but just leave it as the square root of 3625 for right now. And that's actually a perfect, there are perfect squares divided evenly in there, but don't bother with that for right now, okay? We're going to end up plugging this into the calculator eventually anyway, okay? And so something like this guy, if I want the lateral area of this thing, which is really what the question is asking me for, okay? So the question's asking me really for the lateral area. It's pi RL. Well, we know that pi times r, the radius is 40. I actually found that in the process of drawing that triangle, times the lateral area, which is the square root of 3625. And I'm ready to plug this into the calculator already. And the reason for that is because I don't actually need the surface area this time, okay? When you think about the idea of lining this with a funnel filter, this funnel with a cone-shaped filter, there's no piece going across the top of this. In other words, when I put this filter in here, the filter just lines this cone, but is open on top. Okay, and so what the question is really asking here, it's only asking, if I kind of erase some of this stuff, it's only asking for this lateral area because this thing again, it's open on top. There is no base that I need to account for. Okay, and so I just plug this into the calculator. Once again, I'm going to use the pi button on my calculator. So 40 pi times the square root of 3625. And so this gives me approximately 7565.96. And that's square millimeters. Okay? But again, I don't need to find the surface area. I only needed the lateral area for this one.